So let me introduce Scott Holmes from Booz Allen in Maryland. He's been involved with superconducting computing for a long time. Of course, we've had the hope for a very extended period that superconductors could make a huge difference. And there are definite advantages. Many of the devices operate at very low voltage. My concern had always been that after you had, you might have something very efficient, but after you had paid for the refrigeration, it might not be that great. But I am assured that even after paying for the refrigeration, there's still a big advantage in pursuing this. So I'm looking forward to hearing from Scott. Thank you.
Okay, yes, and I work for Booz Allen Hamilton. I'm a consultant to IARPA. I don't work directly for IARPA, and that is one of the reasons. Oh, let's get this on. Can you hear me now? Yes, okay. And that is the reason why I was willing to accept a speaking engagement on October 1st in face of a potential government shutdown. Okay. So I'm going to be talking about superconducting computing. It's an alternative technology. I'm going to go briefly over the problems in large-scale computing. I expect that some of you know about this. Here's a large data center. This one happens to be in Texas. We would see these things, but we had questions. What's going on here? What's happening? How much power do they use? Did a little study, and we found that information about data centers is difficult to get. Partly is that information is considered to be proprietary advantage. However, we have some information here, and there is also more information about open source data centers, such as Facebook. Today, I'm just going to talk briefly about one example. Facebook needed a data center in Europe. Facebook has more users in Europe than it has in the United States. It needed a big data center. This is like a big memory stick here. And so they went looking for a place to site this data center. They found it in Luleå, Sweden. It's just below the Arctic Circle. Average annual temperature, 1.3 degrees Celsius. You get some free cooling. This thing is about 3 times their Prineville, Oregon data center. We estimate that the power is going to be about, oh, there we go, 84 megawatts average to run this thing. It's a beast. It's huge. But even in Luleå, it's close enough to the population centers in Europe that you can run fiber optics down, and it'll work. The problem that we see going forward is that this doesn't scale up very well. People are loading up more and more videos. What are we going to do? You can't, 10 times this, 100 times this. You start, multiple nuclear power plants to support your data center. That's not going to work. We need a better solution. Okay. Let's take a look at large computing systems. There are supercomputers, and we know a lot of information about those. There are not many of them, 500-ish. And they do some significant number crunching, double precision floating point operations. If you look at the power worldwide, not very much goes into supercomputers. Mostly goes into data centers. There's a lot more of these things. It's hard to get information. And there's more integer and memory operations. There's also classes of special machines. OK, so supercomputers. We focus on supercomputers because we can get the information. There's all kinds of information. How much power they use, operating systems, lots of information. We decided to look at what could be done. So we did a feasibility study. First thing we wanted to do was to look at, OK, what's our goal? This is for supercomputers, LINPACK efficiency, flops per watt. And this is the red is the top supercomputers. And the green are the most efficient of the 500 supercomputers. Over time, it's been going up. And there's an exascale goal for Department of Energy. And they're up here. We decided as an alternative technology, you never win by saying you're going to do as good as an entrenched conventional technology. We had to set our goals at least 10 times higher. OK, Here's an energy delay plot of some alternative technologies. Down here is this single flux quantum. That's a superconducting technology. It looks kind of interesting, but refrigeration easily boosts this 400 to 5,000 times, and that puts it back up here. But we know that wiring and leakage losses dominate for these other technologies, and they don't for single flux quantum superconducting technologies. And so there's a chance. Our conclusions when we were looking around was that you can't look at simple things like this. We need better metrics and figures of merit, and that's going forward. I don't know what they are, but we need better ways to look at alternative technologies to bring in, to consider more of these factors. And for us, this full system evaluation is required. We can't just look at a simple little picture. We need to lay out a whole system. So that's what we did. We were looking at 4 Kelvin operation, logic, single flux quantum. There are these little pulses. And the area, the amount is quantized in here. They tend to be a couple of millivolts high, a picosecond wide. They can, if they're wider, then they're also shorter. There's quantized flux in there. So that's our logic. We've got pulses. Memory, there's a couple of different approaches that have been used. If you have a superconducting loop and you get a current flowing in the superconducting loop, that's a 1. And if there's no current, that's a 0. So you can store memory in superconducting loops, or they've got these MRAM type things, magnetic random access memory, where you've got magnetic layers that are either parallel or anti-parallel. And the amount of supercurrent that can go through these changes depending. So you got memory ideas. Interconnects, these little pulses are traveled ballistically on superconducting strip lines. They travel at about c/3, speed of light in the medium. So they're fast, nearly lossless. Looks like we could possibly reduce energy in all the major areas, and thus we looked at it. Okay. Feasibility study, some parameters that we looked at. I'm going to focus on the logic here. Early logic for superconducting computing, rapid single flux quantum, or also called resistive single flux quantum. And that's because they use DC power, and there are resistors that distribute the currents through the superconducting circuit. 90+% of the power in RSFQ gets burned up in these resistors, and these bias resistors. So the static power is very high in this technology. Well, there's new technologies that have been developed. ERSFQ uses a Josephson junction and an inductor to distribute DC current with 0 static power. So boom, that's gone. So we get a factor of 10 to 100 improvement there. There's another technology, RQL, which uses an AC clock on the order of 10 gigahertz or so, and superconducting transformers. Again, 0 static power. Okay. Well, we did a top-down approach. We said, okay, we've got performance that we want from 1 to 1,000 petaflops, and we've got budgets, and let's see if we can get within that. We just use standard refrigeration systems. This one, for instance, is something that you might find in a hospital on an MRI machine. They're in use. You roll this up, you look at, okay, what's our total power budget and cold. This is the cold power, 1.5 watts. That means in the 4K environment, you can dissipate 1.5 watts to do a petaflop per second of computation. That's interesting. Okay. Okay. I'm only going to look at one of the items, memory power. So for each of these, we looked at, okay, this is our budget. Here's our total. And we say, okay, 1.5 watts for a petaflop. Target for memory, 0.4 watts. And what are the available technologies? And we looked at them. One of them was hybrid JJ CMOS, Josephson junction CMOS memory. This was developed by Ted Van Duzer and his group. In the next hall over, Corey Hall. They worked for many years, got some fantastic, more memory than we'd ever had before. But if you throw in the numbers, you get 19 megawatts at 4 kelvins. And our budget is 1.5 watts. And even Ted Van Duzer couldn't say that, 6 orders of magnitude is pretty tough to improve. He retired. Unfortunately, he's gone now. So there are other approaches. You just get stupidly huge numbers. There was one approach, one proposal that we put the numbers together and you get something that might do the job. And so we said, OK, maybe. Rolled everything up, and we came up with the conclusion that this might be possible. However, our priorities for development were memory first, logic, the system, things like how do you do MCMs and superconducting through silicon vias that we still don't have, and things like that, and then interconnects to the outside world. So that informed our development program. OK, so it looks good. Here's power, and here's the existing approaches, and we came up with much better numbers, including all the refrigeration. Great. And how else does it look? Well, this is how it might compare with Titan, which is at Oak Ridge National Laboratory. These are roughly 20 petaflops comparisons. Here they take 8.2 megawatts to run this beast, but that's only the electrical power right in here. That doesn't include cooling and storage and memory, other things. We include everything, and we're 100 times better. By the way, if you're an alternative technology, you need one thing, especially in the early ages, in the early times. You need a good graphic, something that grabs people, something that sells what you're trying to do, something that shows the benefits of what you're doing. This was our grabber slide. OK, challenges. Yes, we have challenges. A little bit about superconducting circuits. For superconducting circuits, inductance and current are the important things. In CMOS, it's voltage and capacitance. So we're different. And another difference is that these things are linked. In a superconducting circuit, you have the flux, the current times the inductance, needs to be on the order of the flux quantum. We're working with single flux quantum things. We need some loops that are too small to hold a flux quantum, so the thing shoots through. We need some that can store a flux quantum. So the inductance and the currents have to be, they're coupled. And yet the switching energy, we can drive the switching energy down. It's the current, the critical current of the junctions times the flux quantum. That's a constant. So it's just proportional. We want small critical currents. We want small currents. The problem is that if you decrease current, you have to increase the inductance. So you need bigger inductors. And inductors take space. So they drive your density down. So we've got these trade-offs that are different from the conventional technologies. We also require fan-out. For fan-out greater than 1, well, that's a lot of time, you require splitters. And a splitter takes 3 Josephson junctions to make a splitter. If you want to go from 1 thing to 64 things, you got a lot of splitter stuff. We're working on that with new devices, but we don't have them yet. So that's a little different. In CMOS, you take it out, OK, boom, you got a lot of fan-out. Low isolation, another problem. Challenges, EDA, electronic design automation. The tools don't work for us. We have a little different technology. Again, inductance is important for us. Inductance is not important for CMOS. And so the tools don't do a real good job. We also, in superconductors, you're used to the magnetic inductance. We're also interested in the kinetic inductance. You take electrons and you accelerate them. And for superconductors, they get going at very high speeds. It takes energy to accelerate the electrons. And that kinetic inductance is sometimes dominant. And that's not usually included in typical, in the existing EDA tools. Placement and routing. Inductance is important. If we make our lines too long, they have too much inductance, the flux quantum gets trapped there. And the concept of, in typical tools, you say you want to go from here to here. It lays a line from here to here. It doesn't care about the inductance and bounding the inductance. The tools don't work quite right. We need to improve the tools. We need to develop tools. That's a lot of work. We also have problems with SFQ designers. There just aren't many. There aren't any programs in the USA. There are programs in Japan and in Germany to develop SFQ designers, but not here in the US. In 1983, when IBM shut down its superconducting computing program, US pretty much shut its programs down as well. So there's few designers. And without good tools, one designer told me that manual design, they have to design circuits manually. And it's like making lace. Well, that's a lot of work. OK. Complexity. We lag semiconductors by about 5 orders of magnitude. Interesting thing is, here semiconductors have been marching up following Moore's law. There are over 1 billion transistors per chip. And here we've been pretty flat over time. The question is, doesn't Moore's law apply to superconductors? Well, we got a key clue here from, this is a recent paper that has talked about different models for technology progress. And they say that underneath Moore's law is an assumption of a exponential growth in money, in markets, in funding. And so we know that. OK, so exponential growth is required. What that tells us is that we need money. We need markets in order to drive up our device counts. Same thing, density. We're about 4 orders of magnitude behind. Recently, our program has helped to improve that, but we're still way behind. System performance. We're so far behind, we don't even know how far behind we are. We have never been able to run a LINPACK benchmark on a superconducting computer. We've estimated that we're about 10 orders of magnitude behind conventional technology. And that's really good, because IARPA looks at that and says, ooh, that's IARPA hard. We like that. They like really hard challenges. Meanwhile, for the rest of us, we look at this and we say, can superconducting computing ever compete with this? This looks really bad. This is kind of what it feels like for us. We're down here, and my God, there's this thing that we're trying to compete with, and it's just going to kill us every time. Well, I have an alternative way to view the relationship with our the established technologies, and it's more like this. Conventional technology needs new solutions. It needs better ways to do things, and they're willing to help, and we learn a lot from them. OK. A little bit about the program that I'm working with at IARPA. So we decided, OK, let's go ahead. Let's build something. Let's build a demonstration system. And we want to find out, is it capable of solving some useful problems? Management. Mark Mannheimer, I support, is the program manager. We've just completed the first year of a 3-year phase 1, and things are going. This is a Notional Prototype. We want to build something in a 4K environment. It's got a CPU and something like a GPU-like thing with parallel accelerators and memory. It's a whole computer, and it can do something. And we're looking to run it at roughly 10 gigahertz, which was, for superconducting computers, not a big deal. OK. Layout, we've got different performer teams working on memory, because that's the long pole in the tent, and everything else. And we're doing, the foundry is Lincoln Laboratory. And we've got a technology roadmap. And just to give you an idea where we're at, we're driving down from, we started out at 500 nanometer line widths, and we're driving down towards 180. So we're far from cutting edge. However, we're using some different materials, and there's plenty to do here. 200 millimeter silicon wafers. This is what our stack up looks like in the early days as an alternative technology. We used to tell people, don't worry, we're like the silicon, the back end of the line. That's the easy stuff. This is trivial. But some differences. you notice that for our stack up in the silicon, semiconductor CMOS back end of the line, the higher up you go in the stack, the larger the features get. For us, the feature size stays the same. That turns out to be non-trivial. It's doable, but non-trivial. There are other changes here. Different materials, niobium. You got to learn how to planarize niobium. It just takes work. OK, systems teams. We've got IBM working on an architecture with many lightweight processors. They're using one of these DC-powered circuit families. Northrop Grumman is the other team. They're working on a RISC-type processor. And they're using this reciprocal quantum logic with an RF clock and power. I'm not going to cover any of the details other than I'll point out this is Northrop Grumman. They've got a CLA carry look-ahead adder core that they've tested. And the power that they've measured on this is 560 nanowatts, 6 gigahertz. OK, well, it turns out that even testing, how do you prove that the thing is energy efficient? Testing, that you've got at 6 gigahertz, that you've got 560 nanowatts, that's non-trivial work. It's different than DC-powered things. OK, cryogenic memory, a couple of projects. Raytheon BBN team, they're looking at a variety of orthogonal STT memory, spin Hall effect memories. This is some of what they look like. Northrop Grumman team looking at spin valve devices with superconducting electrodes. So they've got superconducting electrodes and then these ferromagnetic layers. Details are in the slides. A little bit on related work. This is some of what else is going on in superconductivity. This is a digital RF receiver, company Hypris. The concept is you take in radio frequency stuff, the whole spectrum down at superconducting temperatures. You run it through a very fast A to D, tens of gigahertz, and you digitize everything, and you basically do all the radio and software. This is a commercial system. Here's D-Wave Systems is doing a quantum annealer. They just announced in August 2015 their D-Wave 2. It's got 128,000 Josephson junctions on this chip, 1,000 qubit array. The thing operates at 15 to 20 millikelvins. That's why the box is so big. It's got a huge refrigerator in there. OK, Japanese have also started a 3-year program recently. They're looking at about an 8-bit simplified RISC architecture, simpler thing than we're looking at. However, they are also targeting these data centers. OK, National Strategic Computing Initiative has started recently. IARPA was identified as one of the 2 foundational research and development agencies. If you have interesting ideas, bring them to IARPA. Lessons learned, this is my final slide here. Our lessons. We need some fair metrics. We need something better, better sieve for alternative technologies. We believe that future computers are going to be more diverse in their technologies. And maybe there's some relevant lessons for hiring for diversity that we can apply in our fields. Ramping up requires time and resources, and not just time. And that's the real Moore's law. Government funding alone is not sufficient. We need to find some markets, smaller products and markets to drive these things. Don't go it alone. Use your mother elephant. There's a lot of technology we can piggyback on. Go big or go home. I mean, especially we're trying to attack large-scale computing, and that's where the energy is. And you can't look at little things if you want to save energy. Thank you.
That was very interesting. I've been trying to follow all the advances in superconducting computing, and much of it was sort of not openly discussed very much. And so I'm very glad to hear that there's more going on. So how big was this effort? I mean, it's been going on for years now. Some idea of how many hundreds of millions the government is spending on superconducting computing?
No, I can't say anything about that. But you can think about, okay, you got Lincoln Laboratory. They're setting up fab lines for doing things. Yeah, their fab lines are used for multiple things, but you have some sense for what it takes to run a foundry. Okay. And then you've got multiple teams, including like IBM, Northrop Grumman, et cetera. Yeah. Yes.
More mundane question about one of the parts. You talked about, let's say, Josephson-Amram. Now, usually superconductivity and magnetism don't really go well together, right? So, could you say how this works?
Okay, so yes, they don't go well together. So, if you have superconductivity, when you have superconducting Cooper pairs, or the carriers of these things, pairs of electrons, when they tunnel through, when they pass through magnetic materials, they die out quickly. And but if you have magnetic materials and they're aligned, or they're parallel or anti-parallel, it affects how they behave. And so you got the pair of electrons, and if they're going through a magnetic area, they get kind of hurt. But if then they go through an opposite area, then they sort of get repaired together. So if they're parallel, they get hurt worse, where if it's anti-parallel, it gets better. So this is a case where, yes, the important part is they affect each other. And therefore, you can use that effect to get what you want.
What's a typical superconducting MR ratio? So what is the resistance ratio, or the effect, whatever the effective ratio?
So like the critical current, the amount of superconducting current that you can go through there, you want something double. You want a factor of 2-ish. Yeah, so if you're down around 10%, which we've seen that also, that's more difficult to make use of. You don't want to.
Okay, so let's thank Scott again. Thank you.